Well, hello, everyone, and welcome to our first lesson for calculus. And this one is 9.1. It's an introduction to limits. And the idea of a limit is the basis of all calculus. Like, this is what defines calculus. But it's a simple idea for how many things it really applies to. So I am going to scroll down to the bottom here because I drew a picture at the bottom of the lecture notes, and you could find this lecture notes. You won't find this picture in the lecture tab in my math lab as well, or I'll hand them out in class if you're in class. Okay, so look at this picture. Now, the idea of a limit is as I pick an x value, so as I pick an x value, make sure I got something there, like maybe this 1 right here. Here's our x value, a 1. As I pick that x value, where is the function headed to? Okay, so I look from the left and I look from the right. Like, where is it going? What number is it headed to? So if I get really close on one side and I get really close on the other, where is it headed? I don't care about the actual value at that spot here. I care about how it's approaching there. So I could say, and this is my notation for limit, LIM stands for limit. As our x value approaches 1, where are we headed? We're headed to 2. Okay, so oops, I forgot to put the function right here. Hang on, let me fix this a little bit. So the function, and I'll just label it as the function, is going to 2. There we go. That's better notation. So it's headed to 2. The function is the graph that we have. So if we're looking at that spot right there, I'm going to undo that. Right here, we can see from both sides at that 1, it's going to 2. Now let's move over to this next spot right here at this 2, right? So this one we would write as the limit as x approaches 2 of whatever this function is. Where is that headed? So we look here, and from this side, it's still headed to that 3. And from this side, it's still headed to 3. It is an open dot. And so we don't have a value directly at 2, but the limit is saying as you approach from both sides, where are you going? Both sides are approaching 2. So our answer here would be 2. Okay, we're approaching 2. Even though the function doesn't have a value at that spot. Now, the next one here at 3 has an open dot again, and it has the function up here. Well, this one's a little tricky. We're still looking at oops, let me get my highlighter. What's happening on this side? Where's it headed? And then what's happening on this side? Where's it headed? So we can still see this is headed to 1, right? Both sides are headed to 1, even though the value at that function isn't at 1. So it wouldn't be continuous. It doesn't keep going. So it has a different word, but the limit would still be 1. So we would write that as the limit, LIM, as x approaches 3 of this function is at 1. Okay, and then here, this is our first one that's going to be a little different. So we're looking at this last one here. It didn't erase my pencil. That's all right. It doesn't matter. There it goes. Okay, so at this last one, as I approach from this side, I'm going to 2. But as I approach from this side, I'm going to 3. Am I headed to the same number? No. This means the limit doesn't exist. You're not going to the same number. Okay, so there's a break in the graph. Like, we aren't the same on one side as we are to the other. So if we were to write this one out, the limit as x approaches 4 of this function, we usually write does not exist. does not exist. So looking at this graph is really important before we look at the functions, because you need to visualize what we're doing in the notation as well. So we're just looking to see if both sides are going to the same spot. Do we care if the function exists at that spot? No. So it could have an asymptote. It could have a domain where that's not possible. And we still could say what's happening from one side, what's happening from the other. It's going to the same number. Okay, so I'm going to scroll up to the top of our note packet, and we have kind of this definition here. The limit of the function is going to some number. So you can see, oops, maybe I should highlighter. So you can see right here is the main idea of a limit. Like that's the definition. If the function value is close to a single letter, then whenever x is close but not equal to c on either side of c. It's a little wordy, right? It's just saying, hey, are both sides going to the same number? Yes or no? If so, what number? Okay. And then we have this idea of one-sided, and it's exactly what we just looked at. What are we looking at from this little symbol right here is saying coming from the left. Okay, so you're coming in this way. Where are you going? Okay, and then this one here is saying, okay, as I come in from the positive, where am I headed? Could they possibly be going to different numbers? Yeah, and then the limit wouldn't exist at that exact spot. But you could define like the left side's going to 2, the right side's going to 3, and then the limit at that number C would be does not exist. But you could still define the left side, define the right side, and be able to come up that it doesn't exist. So this bottom part here are just properties of limits. So we'll kind of go through these as we work through the problems, but let's kind of go through them a little bit here. So this first one here is saying the limit of some constant k. Basically, if you have a constant k, it is that number. So if you have a vertical line, then your line is, y equals 2, then your function would just be 2, and everything's going to 2. That's what that's trying to tell you. So if you have a constant, everything's going to that number because it's like a vertical line. Okay, so if you are putting a value into x, you get out just that value. Basically, what we're going to learn is we know if we want to know where we're at a spot, we just put the number in. That's the same idea for a limit. If I want to know where we're at that spot, we just put the number in to the function. Okay, and then this one here, this third one is saying that you could take 2 separate limits and add them. This fourth one here says you could subtract 2 separate limits. The fifth one says you can times by a constant. And again, I'll show examples of why we have this. You can times them. It's saying you could do this one provided the bottom isn't a 0. You can divide, but the limit of the bottom one can't be 0. And then the limit must be, so it's just rewriting this one a little bit different. This one I don't think we actually even have an example of. I don't think we use it. These properties aren't something we focus on a lot, but they are allowed. Like you're allowed to take the limit of one thing, the limit of another, and add them. You're allowed to times them, to subtract them. It's just an overall rule. So let's look at what some of our problems might look like. So problem 1 here says the limit of the function, so it gives us the function 9x plus 5 as x approaches 2. Excuse me. So I could look at the graph of this and see, I could graph 9x plus 5, and I could see what does that graph look like. I don't think I have Desmos on this one. I'm on my iPad, so I don't think I have Desmos on this right now to show it the graph a little bit. But I mean, we could graph it over here if we really wanted to. What we're really going to do is we're going to take the 2 and put it in for the x. And if we don't get a 0 over 0 or a 0 in the denominator or something like that, we can actually just find where that function is at that value. That means the left side's going there, the right side's going there. We know it's there. It's a line, so it has to be going to that value. So 9 times 2 is 18. 18 plus 5 is 23. Okay. So we're here, and the answer would just then be 23. Okay. So well, we could write it up here like this if you wanted. There you go. Either way. So this next one here, this one is -3. Again, this is just a line. So we just put that value in. What is 5 times -3? We're just putting the value in. We get -15. So on these basic functions we've been working with in algebra, lines, x squareds, our parabolas, all of those are just going to give us a value. Even number 3 is just a parabola. So I'm going to put in the 5. So I would have 5 in 2 places. So 5 parenthesis 5 times the 5 plus the 7. Okay, so then I would have inside 25 plus 7 is going to give me 32. I'm going to snail my calculator. 32 times 5 is 160. Okay, and if we graph that, we could see both sides are going to 160. So we're just putting the values in. And it doesn't matter what the function is, like 4 and 5, as long as it doesn't make the 0 in the denominator or a 0 over 0, then we're okay. So for this one, we would have -1 plus 8 on top and -1 plus 2 on the bottom. So that's going to give me 7 over 1 or just 7. Okay, same idea with this number 5. You have a square root, but you're just putting that value in. -8 times -3 plus 1. So a negative times a negative is a positive 24, plus 1 is 25 under the square root. Take the square root and you get plus or minus 5 or 5 for the positive. Okay, so this idea of just plugging them in like this is a huge idea. And as we start to get into these harder problems and you're looking at graphs, it really throws people for a loop. So on the graph, you're looking at where's it headed? Same idea. And it is doing the function and putting the value in just to see where it's at. Okay, so then we start to look at some of the other little rules and some harder problems. So one thing I want to stop and say, this part, I guess it applies next, is if you get 0 over 0, it's called indeterminate form. If I get a 0 in the denominator, no limit exists at that spot. It can't be done. If you get 0 over 0, it can be done, but it's ugly. Okay, so 0 over 0 is not fun, but we'll get there. We'll do lots of examples and you can ask me questions if you need to on those ones. It just is a lot of algebra for those type. So let's look at 6. So this one wants you to use the properties from page 1, and it's basically saying, okay, what if the limit of this function at 3 is 5, the limit of this function at 3 of g at 3 is this, then what is this next part here? So it's like, this is the basis for this problem right here. So it's saying here on the second one, or number 6, if you're putting 3 in, what's the limit of 7 times f of x? Well, if we go back to those rules, it says you can just times them together. So all it's really saying is you take 7 and you times it by that limit of the function at that value 3, which, oh, that came through really ugly. Sorry, I'm writing with an Apple pen. Okay, so really it's 7 times 5, because that's what that value is right here, is 5. So 7 times 5 is 35. That's all that's asking you to think through. So for this next one, number 7, let me change my pencil. I'm going to have 3 times what's f at that 3, f is 5, minus 2 times what's g at 3? It's the -4. And I just calculate that out. I got to remember to times order of operations. So 3 times 5 is 15, minus 2 times a -4 is a positive because it's a double negative. So however you want to think of that, or negative, 8. And then 15 and 8 is 23. Okay, last but not least, this one down, the last one is going to be 2 times the 5 for the F over 3 times the G, the -4 for the G. And again, you're just calculating top and bottom, orders of operation, the 10 over -12. So you do the top, you do the bottom, then you look if you can reduce. We can reduce, it stays negative, and both are divisible by 2, so I would have 5, 6. -5, 6. So if they give you the value, you can still do these problems. You just have to put in the values there. Oh, okay. Now let's look at some little bit harder functions, because we've looked at lines and putting in some pretty numbers. They're all coming out pretty. There's no of the 0 in the denominator. There's no 0 over 0. So this is a piecewise function. And we're putting in this -1. So what this is saying is if x is less than 1, you use this function. If x is greater than or at 1, right? Because equal, then you use this function. That's all a piecewise function is. Okay, so this first one says, what if you want to approach 1 from, what did this little symbol mean again? It meant from the left. That means lower, right? So that means we want to use this function because we're saying lower, the lower side. So it's saying, what's the limit of that left side as you approach 1? So I need to use this function, x to the third. So I'm going to put in the 1 to the third plus 3. 1 to the third is 1. 1 plus 3 is 4. So the left side, as we approach the 1 from the left, it's going to be 4. Okay, now let's look at this one, which is saying, now I want to approach from the other side. So it's coming in from the right side. So that one is going to require us to use the bottom function here. Okay, and so I want to use this function because I'm coming in from the left. So I would then have 3 times 1 plus 1 using that function. 3 times 1 is 3 plus 1 is 4. Oh, so both sides are approaching 4. So what is the full limit as you approach 1? It's 4. Okay. So I looked at the left, I looked at the right. Definitely important too when we get to the asymptotes, because the left and right are very different, and you could see where this would be helpful. Now, what is this last one saying? It's totally algebra. It's just saying, well, what is the actual value at 1? This has nothing to do with the limit. Okay, so what is the value at 1? So 1, we go back, it is using the highlighted one because it has the equal right here. And so we're going to use the 3 times 1 plus 1 function, which is still 4. So the value is 4. It doesn't have to be at the same as the limits, but it is. So that means it's continuous, which is coming up in another section. Like both sides are going to the same thing and the middle's there, right? So it's a continuous function. Okay. So problem 10 is the same idea, so I'm going to skip it. Let's look at problem 11. So 11 is going to be one of our first ones that might have a hole in the graph or an asymptote. So we're going to look at the limit as this function approaches 1. Then we're going to look as it approaches -1 and -5. So let's just put in this value and see where we're at. So we have x approaching 1 here. It's not from the left, it's not from the right. We'll do a lot of those in the next section as well. So we would have 1 squared minus 8 times 1 plus 7 over 1 minus 1. So I'm going to have 0 on the bottom for sure. 1 squared is 1, minus 8 plus 7 is also 0. This is indeterminate form. And that means you can't tell. That's right. Indeterminate form means you can't tell. Let me move my picture. There we go. And so we have to do something. So we either have to factor or we have to use that idea of rationalizing the denominator, but we do it backward and we rationalize the numerator. So for this one, can we factor? So let's look at the top function. Does it factor? So we're looking at that 7. Values that multiply to 7 is just 7 and 1. And in how can I get the -8? If they're both negative, they would multiply to that positive 7, but they would add to a -8. So this would factor into x minus 7 and x minus 1. Again, I'm sorry, it's a little bit of chicken scratch with my Apple Pen. Okay, over the x minus 1. So you can factor. Do you have a common factor that you can cancel? You do. Ta-da, these ones cancel. So then what I do is I go back to this function of the limit as x approaches 1 of the x minus 7. Okay, what does that equal? Because I can cancel those factors. And then I will have it in a determinate form. So 1 goes in there and I get -6. Ta-da! So a lot of ours are just factoring. They get a little harder though, for sure. Okay, so problem B and problem C are just putting the value in and getting an answer. It's just a fraction. So you just put in -1. It's not going to give you 0 over 0 because we just did that one. Okay, I'm going to move to 12. I don't think we need to put in the values. You can do that. It's just going to be do your top, do your bottom, forms a fraction, reduce your fraction. Okay, so here's a weird one. So let's look at from that left side for the first one. So as it approaches 2 from the left side, we're going to have to graph this one. Okay, so couple ways we can do this. We can put in some values close to that left side. That will work for us to see where it's headed. So what I mean by that is you can do a little chart. Oops, I'm on highlight. You can do a little chart, X, Y, right? And what is a number really close to 2 from the left would be like 1.9. To get closer would be 1.99. And closer would be 1.999. So we can see like where it's headed, right? So I'm going to get out my calculator because I want to. So 1.9 minus 2, that's this top part right here. 1.9 minus 2, maybe I'll write that out for y'all. So right here I'm doing, gosh, I didn't leave myself any room. I'm doing the absolute value of 1.9 minus 2 divided by the 1.9 minus 2. Okay, so I get a negative on top, but it changes to a positive because it's coming out of that absolute value. It was a negative 0.1 on top, and then on the bottom it was oops, and this had the absolute value, and the bottom was a negative 0.1. So that becomes positive on top, and the bottom becomes negative. So it's going to be 0.1 divided by 0.1, which is going to 1, but it's a negative. Blah. Okay, 1.99. 99 minus 2 is 0.01. And 0.01 divided by 0.01 is another -1. You get this idea. It's all going to -1 on this one. Okay, and then this next one, if we are going from the positive side, then I might think of, okay, it's going to be maybe 2.1, right? To get closer, it'd be 2.01 or 2.001. So let's see what happens there is the top would be 2.1 minus 2, which over the 2.1 minus 2, and then this is in the absolute value. That's going to stay positive, and the bottom is positive, so this is going to positive 1, okay? So this one's going to positive 1. So I can put in values getting close, or I can graph it and look at the graph. What is it doing is it's getting close. So I will pull up Desmos in just a second. We'll look at that too. So what is the full limit? Well, if the left side's -1 and the right side's 1, it does not exist. They have to be the same. You're not going to the same spot on both sides. So I'm going to unshare my iPad and share my screen real quick on my computer. And I will open us our Desmos here. And let's put in, my Wi-Fi is being a little slow. Maybe. Huh. Here, Wi-Fi. Darn it, it's really not wanting to come up. Okay. So if we put the graph in, you can put it into Desmos. It's going to go opposite. Let me see if I have Desmos on. I have it on maybe I'll just share my phone. Sometimes you can do different things. So share, and I have Desmos on here. If you don't have the Desmos app, I would completely get that. Oh, it's not going to let me share my phone. Am I on the wrong Wi-Fi? No. Okay, we try again. Oh. At some point in my life, I will have things in the right order. I don't even know if you need to see this graph, but it's coming. Okay, so I'm on my phone and I'm here on Desmos. So I would type in the graph that we had, which was, I'm going to use a parenthesis, absolute value of x minus 2, and then in the absolute value in the parenthesis, and then we have a division, and the bottom was just x minus 2. So there you go. There's the graph, and that's why it doesn't have a limit at that spot at 1 is because, or no, yeah, was it 2? Excuse me, 2 there. Was because it's coming in on one side at negative and other side positive. So you could see it from the graph, but do it on paper as well. And then I am going to open the next class with a warm up of a really hard one, or in the next class we'll do some harder problems similar. Okay, that's all I got for this lesson.